Good afternoon, guys. The aim of this video that Mrs. Rudy and I have talked about is to help you get into the information that's related to Chapter 11. We're going to skip Chapter 10 for the time being. We're going to do 11. We'll come back to 10, and we'll jump to 12. We've done a couple of switches of chapters that make a little bit more logical sense to us. So today what I'm going to do is begin a series of a couple videos that show you the various types of chemical reactions that we're aware of and that can occur. And these reactions are typical of what you'll see in Chapter 11. You normally have the opportunity to work right in the lab, but unfortunately in our situation now, you can't do that. So what I'm going to do is walk you through the lab, do it, give you data, tell you a little bit about the experiments themselves, then we'll do a little follow-up later on. So the first experiment I'm going to do today is one that we call a combination or synthesis reaction. So let me bring up this little graphic to show you the title. Combination or synthesis reaction. And we're going to be mixing iron with oxygen. And we're going to form an iron oxide. So the plan is to do that reaction, measure things, show you the data, give you opportunity to take some notes on it, and then eventually we'll do a little follow-up evaluation on it. So to start off, what I'm going to do is take a little bit of steel wool, which has been made of iron, obviously, and you probably have seen this. You might have scrubbed some pots and pans with it, maybe done something in the shop with it. But it has iron in it. I'm going to take it, pick it up with tongs, and I'm going to heat it and let it react with oxygen in the air. Now, normally it's going to react with oxygen in the air, but it's going to be real slow, and it will take a little time for it to react. So what I'm going to do is I'm going to take it and speed the reaction up a little bit by adding some heat. Let me turn on a Bunsen burner. Got a nice blue flame here. I'd like you to note that the color of the steel wool is kind of a silvery gray. You can see it against my shirt there. Let me take it with the tongs and hold it in flame for you. Let me aim this a little bit better for you. Okay, so here we go. As I'm doing this, the reaction is up about 500 or 600 degrees Celsius, so the iron is actually reacting very vigorously, and some of it is actually breaking off and falling onto the tray that I have here. What I'm going to do, though, is do that reaction for you again, but this time I'm going to do some weighing of the materials. So let me get you a sample of what I'm going to do here. I'm going to turn off the burner. Let's first of all take a look at the steel wool. It's fairly cool at this point, but let me hold that up. And if you compare the color of this to what I had originally, you might notice a difference. And in fact, there's actually a spot right about here on the piece of steel wool near the top of the tongs there, where the original color is there, but the color surrounding it is different. So obviously the steel wool has changed chemically, and I've got a new type of iron oxide produced here. I'll bring it up a little closer for you. You can see the difference in color. Okay, now let me take another piece of the wool, and I'm going to weigh this one. So I'm going to take my wool, piece of wool, put it on a weighing pan, and I have a very sensitive balance that I borrowed from Dr. Berlardi's room. It's back here. I'm going to weigh the steel wool in the pan. I'm going to first of all start off by weighing just the pan. And this is typical of our electric scales, where you can press the tare button and make everything go to 0. It's now reading zeros. Let me take a piece of steel wool, open the little door on the side, drop this on top. And what I'm going to do is I'm going to write down the mass for you, 0.3604. Let me hold it up so you can see the number. 0.3604, and that's my initial mass of steel wool. And then we'll put it in the flame and see what happens. We saw the color change. So I'll take out my wool, put it in the tongs, light the burner. Again, as I'm starting off, the steel wool has a kind of a silvery gray color to it. As you saw before, the steel gets really hot. Again, very high in temperature. And pieces have broken off. They've fallen now on the tray. And the piece of wool is once again changed in color. That suggests it suggests a color change has occurred and a chemical change therefore has occurred. So I'm going to put it on the tabletop on a little pad here for just a second so it cools down. I don't want to touch it while it's really, really hot. Put the tongs aside. I'm going to put my hand near it and it feels pretty good. It feels pretty normal to room temperature. We'll take it, we'll put it on the pan once again, just drop it on top. Now, some pieces of steel wool have fallen off and they're on the tray, and I want to put those onto the pre-weighed pan. So what I'll do, I'll tilt the tray a little bit, get some of those pieces of steel wool, fall to the corner here, dump them on. Put the pan back in here with the wool, close the door, and here's my new mass, 0.4226. And I'll give this number to you up close again. And so now my new mass is 0.4226. That's the final mass of the steel wool. The initial mass is at the top, and it'd be a good idea if you put these two numbers into your notebook. And then what you'll be doing is you're going to try to find eventually the difference in mass. And then also try to figure out why is there a difference in mass. That's one of the aims for our experiment here. Not only is there a difference in mass, but why is it there? Okay, now I'm going to stop the video and get things ready for my next experiment. So I'll be back in just a couple seconds. Okay, for our second reaction, the type of reaction that I'm going to be showing you here is going to be called a decomposition. We've just finished composition or combination. Now we're going to do the opposite. We're going to take a compound and break it apart. We're not going to make one, we're going to break it apart. And the reaction that we're going to do for decomposition is taking hydrogen peroxide, H2O2, adding a catalyst to it, and getting it to break down into water and oxygen. Now, normally, the reaction you just saw takes place at room temperature. So if you have a bottle of hydrogen peroxide, and this is industrial peroxide that I have here, it's automatically breaking down. it's going to be eventually becoming water, and oxygen gas will come off from it. If you have a bottle of peroxide at your house, after a period of time, maybe a year or so, you don't have hydrogen peroxide. You probably have mostly water in the bottle, and it's probably time to renew it. Okay, so for our equipment now, I have my peroxide, and I poured some into a beaker. I'm going to take and put 5 milliliters into my graduated cylinder. I actually have 6. I'm going to pour it into a very large test tube. This is an ignition tube. It's thicker glass. I'm going to put it into my clamp. Bring the clamp all the way down to the support stand's bottom. Clamp it up a little bit. I have a little petri dish at the bottom here. I think I got some peroxide on my finger. I'll just wash that off. If I don't wash it off in a couple of minutes, it'll start to sting. The other compound that I'm going to now use, and you actually don't see this in the chemical reaction as a ingredient, but it's going to be a catalyst. It's going to be there, but we're not going to lose it. It'll be helping the reaction go faster, but it'll still be there at the end. It's a black substance. Came from this bottle. It's called manganese dioxide. I'll bring the bottle up close for you. Manganese dioxide. Formula is MnO2. I just need a little bit. So I'm going to put that manganese dioxide into the reaction test tube. I'm also going to check temperature. So over on the side here, I have a little temperature probe, and it's reading room temperature right now, which is about 22.8, 22.9 degrees Celsius. Actually, it's reading 23 right now. If I were to touch this probe and hold it with my hand, it would automatically go up. So it's reading pretty close to room temperature. I'm going to put that into our peroxide just to see what the temperature of the peroxide is. So it's down in the graduated cylinder. It takes about 10 seconds for the temperature probe to register. And it's reading 22.9, 23 degrees Celsius. So it's pretty close to the room conditions also. Okay, so the next thing, I'll dump in the peroxide solution. Then I'm going to dump in my catalyst, the manganese dioxide. I'm going to put the manganese dioxide in with a scoop so I don't use too much. I want to try to use what's probably equivalent to a match head. Okay, so let's dump in our peroxide. Here's the manganese dioxide, black crystal powder. We get an immediate reaction, and I'm going to put my temperature probe in just to see what the temperature is doing. Stir it just a little bit. The temperature probe is made of stainless steel, so it's fairly impervious to the liquid, and I'll clean it off at the end. And our temperature has gotten up a little bit. It's registering here about 46 degrees. Oh, 50 now. And it's still rising. Now, from the top of my test tube, there's some vapors coming out. Let me test the stuff coming off. I'm going to take a splint, light it up, put it near the top. I'm going to pull the thermometer or the temperature probe out for just a second. I'll put this near the top, and you can see right away that the splint is burning faster. So oxygen is coming off. The splint's able to burn faster. The presence of the oxygen causes that to happen. It's still bubbling.